Alrighty, so let's have a look at the multiple choice questions from June 2010. So starting off with some advanced mechanics. Which of the following statements is correct? The force acting on an object is equivalent to its rate of change of momentum, or its impulse per second is the correct one for, because it's the force is the rate of change of momentum. The change of momentum is an impulse, so it's an impulse divided by time. Okay, so graph shows how a force on a glider of mass 2,000 kg changes with time as it is launched from a level track using a catapult. Assuming the glider starts at rest, what is its velocity after 40 seconds? Well, its change in momentum is the area under the graph, which would be half times by 5,000, which is the height, times by 40. But we want the change in velocity, so that will be that divided by the mass, times 5,000, times by 40, but divided by 2,000, so we can cancel all those. That's over 4, so that ends up being 10 times 5, so 50 meters per second. Let's calculate that. A gas molecule of mass m in a container moves at velocity v, makes an elastic collision at right angles to the walls of the container. What is its change in momentum? So initially it's going at v, and it will come out at minus v because its kinetic energy has to be the same because it's an elastic collision. So the change in momentum would be m delta v, which would be m v minus minus v, so it would be 2mv, which is d. The mass on the end of the string is whirled around in a horizontal circle at increasing speed until the string breaks. The subsequent path taken by the mass is, so if it's travelling horizontally, initially it would be travelling in a horizontal direction, essentially a tangent to the circle when the string broke, but then it would accelerate towards the ground, so following parabolic motion towards the ground, so it would be a parabola in the vertical plane. So the horizontal velocity would be unaffected because the g would be acting down, but it would be accelerated in a vertical direction, so a parabolic path in a vertical plane. So in this question we've got a particle of mass m in a circle of radius r at uniform speed, and it takes t for each revolution. What is the kinetic energy of the particle? So we know that in circular motion the time period, so in this case t, is given as 2 pi over omega. We know that omega equals v over r. So we can rearrange that to omega equals 2 pi over t, which implies that v equals 2 pi over t times by r, so 2 pi r over t. So we know that v squared would be 4 pi squared r squared over t squared. So we know that the kinetic energy would be half m times that. So times by half, that gets rid of that. Pi squared r squared m over t squared. So it's got a t squared on the bottom line, so we know it's not that one. We've got 2 pi squared mr squared here, so it would be d for this one. A body moves in simple harmonic motion of amplitude 0.9 and period 8.9 seconds. What is the speed of the body when its displacement is 0.7? So we know that v is equal to 2 pi f square root a squared minus x squared, and we know that f is 1 over t, so it would be 2 pi over t square root of 0.9 squared minus 0.7 squared, which when you type that in comes out as 0.399 blah blah blah, so that would be 0.4, so answer C. Okay, which graph A to D shows the variation of kinetic energy with displacement for a particle performing simple harmonic motion? So when displacement is 0, we should have maximum kinetic energy. So that's going to eliminate answers C and D straight away because they don't show that. And then if we think what's going to happen, so as the object approaches the equilibrium position, the force acting on it is going to be reducing because, say for instance, the extension of a spring will be smaller at that point, so the rate of change of velocity will be decreasing, so the rate of change of kinetic energy would therefore also be decreasing, and it would always be decreasing the gradient from the initial position because the force is getting smaller every time, so that would make it A. Okay, so let's scroll down for question number 8. Time period oscillation of a simple pendulum length L is the same as the time period of oscillation of a mass M attached to a vertical spring. The length and mass are then changed. Which of the row A to D in the table give a simple pendulum with a time period twice that of the spring oscillation? So let's think about how we get time period. So for a pendulum, we're going to get root L over G, and the time period for your mass spring system is going to have your M over K, and then obviously that's going to be multiplied by 2 pi. So if we want the pendulum to have twice the time period, we'd have to multiply L by 4. So that's not one of the options, so we must be doing something to both equations. So if we multiply the pendulum equation by 2, so have 2L, and then halve the mass in the second one, we'll end up with a difference, which is a multiple of 4. So that's what we've got here in line B. By halving the mass and doubling L, then your time period will end up being double because of the fact there's a square root in there. Alright, so question 9. A projectile moves in a gravitational field. Which one of the following is a correct statement about the gravitational force acting on the projectile? The force is in the direction of the field. The force is in the opposite direction to that of the field. The force is at right angles. For a start, no. No. The force is most certainly in the direction of the field. So if you think the field lines with gravity are acting towards the centre, so they're like this, and an object would experience like a force in that direction too. So we know it's parallel there. Gravitational potential difference between the surface of the planet and a point P 10 meters above the surface is 8 joules per kilogram. Assuming it's a uniform field, what is the value of the gravitational field strength in the region between the planet's surface and P? So the field strength is dV over the distance, so it's going to be 8 by 10, so it'd be 0.8 newtons per kilogram there, which would give you answer A. Okay, question 11. An artificial satellite of mass m in a stable circular orbit around a planet of mass big M. Which one of the expressions gives the speed of the satellite? So we want V. So for a satellite, we know that mv squared over r equals g m over r squared. Let's cancel those, So V ends up being the square root of gmm over r, or gm over r to the power of a half, which is that one. Alright, a small object O carrying a charge of plus q is placed at a distance d from a metal plate that has an equal and opposite charge. The object is acted on by an electrostatic force F. Which one of the following expressions has the same unit as F? So we're looking for a force. So electrostatic force is QQ over 4 pi E0 r squared. So we're looking for units of coulombs squared over distance squared, and then the unit of permittivity of free space. Let's find it on the formula sheet. Where's 8.85? 8 is in farads per meter, which is E0, which you can see there. So we need something with a Q squared on the top line, which is all of them, so it doesn't help. We need a distance squared on the bottom line, which is going to be helpful here. So we can get rid of that one and that one because they don't have d squared, and you should have E0 on the bottom line because you can see it's on the bottom line of this equation. So it's going to be this one down here. Diagram shows two charges, plus 4 and minus 16 millicoulombs, 120 millimeters apart. What is the distance from the 4 millicoulomb charge to the point where the resultant electric potential is 0? So we're looking for essentially where 4 over k d1 squared is equal to 16 over same constant d2 squared. And we're trying to solve for d1, and we also know that d1 plus d2 is 120 millimeters. So at this point you can solve these by substituting in and solving for d1, but I prefer not to do that, so let's cancel the 4's. And what we've got here is essentially two square numbers, so if we square root both sides, we end up with 1 over root k d1 is equal to 4 over root k d2. Really should have just cancelled the k's earlier, that's annoying. So you end up with d2 is equal to 4 times d1, and so essentially what we have is 5 d1 is equal to 120 millimeters, so you know that d1 is that divided by 5, which would give you 24 millimeters. So it's useful spotting you've got all the squares on there, so you can solve this without doing a substitution, which is quicker. Okay, question 14, the worst question in this exam by the statistics anyway. I think something like only 30% of candidates got this one right. So we've got 4 point charges at corners of a square side 2a. What is the electric potential at P in the centre of the square? So first of all, if this is 2a, this distance here is going to be a. So all of the charges are a distance of square root of a squared plus a squared, so they're all a distance away of 2a squared. And we're interested in potential, so we're not going to be interested in d squared, we're only going to be interested in d. So let's think. Some of these are going to end up cancelling out because they're essentially opposite and pulling in the opposite directions. So let's forget about those. So like these two are trying to go the same way. So we're going to end up with, so the pull from this plus q would be, oh, we want the potential, so yeah, 4 pi E0 root 2a squared. And we've also got this one working with it, so you're doubling it. So that's going to cancel with that one. You end up with q over 2 root 2 pi E0 a. which is 2 root 2 pi E0A is answer number A. So that's this one. So the key thing is working out the fact that these two cancel out because they're essentially pulling in opposite directions, whereas these two here on the corner, this one here and this one here are working together. So essentially, they're working in the same direction. So you add their two potentials together, which is why here you've got the 2. Okay, a 1 microfarad capacitor is charged using a constant current of 10 microamps for 20 seconds. What is the charge? Well, the energy is finally stored by the capacitor. So the charge would be 10 times 20 times 10 to the minus 6. What's that? 200 times 10 to the minus 6, or 2 times 10 to the minus 4. The energy stored is half q squared over c, so 2 times 10 to the minus 4 squared divided by 2 divided by 1 times 10 to the minus 6. And you end up with 0.02, which is answer B. So what we are using here is half q squared over c. We've got q, we've got c, so we can calculate it and you get that value there. 2 millifarad capacitor is used as a backup, has a potential resistance of 5. Twice constant current of 1 times 10 to the minus 6. And can be used until the potential difference across it falls by 10%. How long can the capacitor be used for? What are we going to do? Okay, so if it's forward by 10%, it's going to end up with 90% of its original value. So the first thing is to work out what its initial charge is, which is going to be CV. So that was going to be 2 times 10 to the power of minus 3, because that's the C, times 5, gives you 0.01 coulombs. The change in Q, if it drops to 90%, is going to be therefore 0.001 coulombs, because it's lost 10% of its energy. And so time would be the charge divided by the constant current, 0.001 divided by 1 times 10 to the minus minus 6 gives you 1,000 seconds, which would be that one. So number 16, complete. When switch S in the circuit is closed, the capacitor is charged by the battery to a potential difference of V0. Switch is then opened until the capacitor PD decreases to half of the initial one, and at which time the switch is closed again and charged back to V0, which best shows how the potential difference across the capacitor varies with time after S is opened. Okay, so PD is going to decrease and then increase, which all of those graphs show, so that's not as simple as that. So its discharge time should be the same as charge time. Again, both show that, so that's not going to be helpful. Okay, so let's think. So the potential difference is always going to decay like this, because we think of it when it's discharging, the graph looks like that. So we're looking for that in the first section. So that's going to eliminate that one, and I think it's going to eliminate that one. And then the charging graph, what am I doing? What an absolutely ridiculous graph. Charge graph looks like that, so we're looking for that section in there, so that's going to give you A for question number 17. Alright, question 18. A capacitor discharges through a resistor. It loses 50% of its charge in 10 seconds. What is the time constant of the capacitor resistor circuit? So we're using the 10... Alright, we're doing this with charge, aren't we? Right, it doesn't matter. So a Q at a time is Q0 e to the minus t over the time period. So it's lost 50%, so we essentially end up with 0.5 equals e to the minus 10 over t. So we're going to take the natural logarithm of both sides. So log 0.5 is equal to minus 10 over t. Log 0.5 is going to be a minus number, so that's going to be fine. So that, and then divide by minus 10. Then flip it, gives you 14.4, so approximately 14 seconds. One is what I was going for, not circle D as well. The diagram shows a rigidly clamped straight horizontal current carrying wire held midway between the poles of a magnet on a pan balance. The wire is perpendicular to the magnetic field direction. The balance was zeroed before the switch is closed, so the balance is not going to measure the weight force of the wire at all. It reads 12 grams after the switch is closed, which must mean when the switch was closed there was a force acting down from the wire. If the current is reversed, that force is now going to be acting upwards. So if it was just reversed, it would measure 112, and it's doubled, so it's going to measure double that, so it should measure 224 grams. So that is going to give you A. Electron moving with a constant speed enters a uniform magnetic field at right angles to the field. What is the subsequent path of the electron? So we've got electron going this way, and then essentially enters at a right angle to the field. So the force is always going to be perpendicular to its motion, and the force is acting perpendicular to the velocity, so the velocity won't change. So we've got the conditions of circular motion. When a charged particle is moving perpendicularly to the field, we get circular motion there. A jet of air carrying positively charged particles is directed horizontally between the poles of a strong magnet, as shown. Which direction are the charged particles deflected? So the field lines are going across like this. So we've got essentially the flow of positively charged particles going into the page. We've got the field itself going across in the plane of the page. So when we apply Fleming's left-hand rule, we're going to end up with a force that way, so the charged particles are going to be deflected downwards in this case. Which one of the following could not be used as a unit of force? Okay, so in terms of magnetic fields, we have F equals BIL, which is a Tesla amp meter. So that one can. We also have like mass times acceleration here, so that's a force. And we also know that energy is a force times distance, so a force is energy over distance, so that one is, so it will be this one here, B, which is not correct. The graph shows how magnetic flux passing through a loop of wire changes with time. So we've got a fixed rate of change of flux. The magnitude will be the gradient of the graph, because EMF is the rate of change of flux, so that's only this one. A coil rotating a magnetic field produces the following voltage waveform and connected to an oscilloscope. Same oscilloscope settings, which one of the following waveforms would be produced if the coil were rotated at twice the speed? So if it's twice the speed, we've got double the rate of change of flux, so you expect double the EMF, so you should end up with double the EMF or double the voltage, so the amplitude should be double, and you should also get twice the frequency because you're doing twice as many oscillations per second, and that is shown by C. And then final question. A 230 volt 60 watt lamp is connected to the output terminals of a transformer which has a 200 turn primary coil and a 2000 turn secondary coil. So that means it's a step transformer. So on the primary side it would have been 23 volts because it's then stepped up to 230 volts. Primary side is connected to an AC source with a variable output PD. Lamps light as normal brightness when the primary coil is supplied with an alternating current of 2.7, which would be stepped down to 0.27 amps. So from this we get the power in was 23 times 2.7, 3 times 2.7, because it's IV, which is 62.1 watts. Power out, it tells you in the question, was 60 watts. So the efficiency would be 60 divided by that times 100, which gives you 97%. Okay, and that is the end of this paper.